Beyond the asteroid belt, at the gateway to the outer solar system, moves the largest and most massive of the planets. It is fitting that this giant world should share its name with the most powerful of the ancient Roman gods. Jupiter, ruler of all the gods and divine protector of Rome. To the Romans, he was both an indispensable ally in their military efforts and a life-giving provider of rain for the farms and vineyards. Jupiter Optimus Maximus, the greatest and most powerful. To the naked eye, the source of that mythological tradition is the fourth brightest object in our sky after the sun, the moon, and Venus. To the ancients, Jupiter was a bright, powerful beacon in the night sky. But to us, with all the advantages of space probe photography and computer-enhanced images, this is Jupiter. To grasp the immensity of Jupiter, our home planet can be used for comparison. 11 Earths would stand side by side across Jupiter's equator. Even more dramatic is the difference in volume. Jupiter's sphere would swallow up 1,300 globes the size of Earth. This huge body spins a full rotation every 10 hours. And Jupiter outweighs all the other planets, moons, and debris in the solar system combined. Its powerful gravity tugs at the other planets and their moons, and even controls the orbits of some comets. Jupiter is a kind of mini solar system. 4 of Jupiter's moons, called the Galilean satellites, are the size of small planets.
At 300 times the mass of the Earth, Jupiter contains most of everything that's in the solar system that's not in the sun. And yet, Jupiter's got a volume more than 1,000 times the Earth's size. And so this means, and it's been known for centuries, that Jupiter is not made of the same heavy, rocky materials that make up the terrestrial planets, like, of course, the Earth, and Mercury, Venus, and Mars. All the Earth-like planets are themselves very different and hostile environments, but they do share some characteristics. They're all small, dense planets with solid, rocky surfaces. And in fact, you could land a spacecraft on those surfaces and with suitable protection, get out, walk around, see what they're like. This isn't the case with Jupiter, however. It's a giant planet with a low density. Its material then is more like water than rock. That's because it's made up of lightweight materials, hydrogen and helium, the same kind of thing that makes up most of the sun. Now, Jupiter may have a small rocky core deep within it. We just don't know. But most of the interior of Jupiter is liquid, with a thin, gaseous atmosphere laid on top of that. The beautiful and striking bands and the great red spot we see there were actually first observed 300 years ago or so by Cassini. We now know that these are simply complex motions in Jupiter's cloud deck. The real causes, of course, may be deep below that cloud deck. Well, the other outer planets, the large ones like Saturn, Uranus, and Neptune, are also then mostly liquid giant planets. And this allows us to distinguish between the large Jovian planets on the one hand and the small terrestrial planets like the Earth on the other.
Probably the large sizes and low densities of the Jovian planets are related to the deep cold of space at their greater distances from the sun. They were able to hold on to the light chemical elements of hydrogen and helium, which were so abundant in the cloud which spawned the solar system, but which were boiled away from the inner planets by the sun's heat. The innermost of the Jovian planets, Jupiter itself, is still more than 5 times farther from the sun than is the Earth, at a distance of just over 5 astronomical units. At this greater distance, the sun's gravity is weaker too. So, moving at a slower velocity than Earth and with a greater distance to travel, Jupiter takes 12 years to orbit once around the sun. Despite their large sizes, all the Jovian planets rotate quickly. Jupiter in less than 10 hours. This fast rotation and the planet's low density cause Jupiter to be noticeably oblate or flattened. Even with the most powerful telescopes for the ground-based observer, this is the face of Jupiter. It wasn't until the Pioneer missions that a clearly defined close-up view of Jupiter became a reality. On the second day of March 1972, Pioneer 10 began its journey from the Kennedy Space Center to Jupiter, 20 months and 500 million miles away. A year later, in April 1973, Pioneer 11 left the pad and followed its sister spacecraft. Pioneer raced toward Jupiter at a rate of 1 million miles a day, passing the moon in just 11 hours. But even at that speed, Jupiter was still almost 2 years away. Beyond Mars, Pioneer approached the asteroid belt. Before Pioneer 10, the asteroid belt was believed to be a region where enormous boulders collide and grind together, creating a 40,000 mile per hour sandstorm and possibly an impenetrable barrier between us and the outer planets. But Pioneer actually encountered very little space dust in the asteroid belt and continued on its way, unharmed and alone, in the vast emptiness between the asteroid belt and the outer planets. The Pioneers followed the commands of the mission controllers at NASA's Ames Research Center near San Francisco. Using a two-way radio link, Mission Control transmitted commands to Pioneer, and the spacecraft sent back a constant flow of scientific observations and information about its condition.
We just received a stand clear message. Roger. Arctic Command, verify command stack loaded. Block message number 9. First command, ID Whiskey 2, time 141032.8. Roger, copy. We're enabling message at this time.
Finally, in late November 1973, 20 months after launch, Pioneer closed in on Jupiter. Every hour carried the spacecraft 20,000 miles closer to the massive planet, and even then, it was being mercilessly cooked by the incredibly severe radiation which surrounds Jupiter and its moons. Because of the dizzying speeds of the spacecraft and the planet itself, the first electronic camera scans couldn't immediately provide a pretty picture. The early images had to be corrected for distortion, but even the first stage of prettying up gave a tantalizing hint of the spectacular images buried in the raw data. Later, the tapes would go through computerized image enhancement at the University of Arizona, and eventually, a portrait of Jupiter emerged to challenge the most imaginative artist. Meanwhile, the pull of Jupiter's gravity had increased Pioneer's speed to a fantastic 82,000 miles per hour. And it was exactly this crack-the-whip turn which would fling both Pioneers toward the edge of the solar system and beyond. From Earth, only the full phase of Jupiter can be seen, like a full moon. But Pioneer was now viewing a sight never seen by any human, the crescent Jupiter. On the television system, the images were rapidly becoming smaller. Using energy literally stolen from Jupiter, Pioneer departed more than twice as fast as it arrived. Pioneer 11 rushed onward to reach the next outer planet, Saturn, with its glittering and mysterious rings, in September of 1979.
Since the two Pioneer spacecraft gave us our first close-up view of Jupiter, or of any giant planet for that matter, we've learned a great deal. We've seen multicolored bands and belts and learned that they're clouds at different temperatures and elevations and smeared by Jupiter's rapid rotation. But more importantly, we've learned that Jupiter has a strong magnetic field that traps charged particles from the solar wind to create radiation belts, like the Van Allen belts around the Earth, but 1,000 times more intense. Some of the Pioneer instruments, in fact, almost failed because of this unexpected radiation. And had there been any astronauts aboard, the radiation would have proved fatal in less than a second. Still, the Pioneers were only inexpensive scouts sent to prepare the way for the later Voyager mission. Pioneer's spinning, scanning method of photography took upwards of a half an hour just to take one image, and it only took a few hundred pictures over the few days of closest approach. The more sophisticated Voyagers took tens of thousands of snapshots over a period of months with far better resolution and detail. For example, photographs of Jupiter's largest satellites taken by Pioneer were hopeless blurs. They still told us more than we'd ever learned through telescopes on the Earth. Yet Voyager photographed these satellites with breathtaking clarity. And as a result, the Voyager mission gave us 4 brand new worlds to study. Technically, these are moons, of course, because they do orbit Jupiter. But geologically, they're planets in their own right, with identities as unique as those of Mercury, Mars, or any of the other terrestrial planets.
Voyager 1 and an identical spacecraft, Voyager 2, were launched by NASA in August and September of 1977. Both were targeted for Jupiter and Saturn and a dozen of their moons. Flying a shorter and faster route, Voyager 1 was launched 2 weeks later than its twin, but arrived at Jupiter 4 months sooner. Using Jupiter's enormous gravity, they were hurled into a Saturn trajectory. Each Voyager spacecraft is equipped with instruments for conducting 11 science experiments at the giant outer planets and their satellites. These intricate, automated spacecraft were designed, assembled, and tested by the Jet Propulsion Laboratory, which manages NASA's planetary exploration program and controls the Voyager mission from Pasadena, California. As the Voyagers approached Jupiter, the planet tracking instruments, TV cameras, infrared and ultraviolet spectrometers, and a photopolarimeter observed the primordial atmosphere at different wavelengths. Later, as Earth and Sun disappeared behind Jupiter and then re-emerged after 2 hours of eclipse, the spacecraft recorded the scattering effect of the planet's atmosphere on solar radiation and on its own radio signal. Jupiter has an immense magnetic field flattened into a vast disk, which traps high-energy protons and electrons. Voyager's magnetometers and radiation detectors observed the interaction between the radiation belts and Jupiter's inner moons. One moon in particular, Io, is the most interesting of the 4 large planet-sized moons. Between Io and Jupiter, there exists a magnetic link called the Io flux tube, a phantom-like cylindrical zone where charged particles spiral along the magnetic lines of force and intersect Io with a 5 million ampere current. This flux tube exerts influence on the powerful bursts of radio emission from Jupiter. After the Sun, Jupiter is the noisiest source of radio signals in the sky. Voyager's instruments analyzed the potent bursts of energy equivalent to millions of strokes of lightning. Yet another consequence of the interaction between Jupiter's radiation and Io is the presence of a cloud of sodium vapor surrounding Io, which had been detected spectroscopically from Earth. The Voyager scientists never suspected that this cloud would foreshadow one of the most exciting Voyager discoveries of all, that Io is covered with active volcanoes. Like Pioneer, the Voyagers used the pull of Jupiter's gravity to propel them out of the Jupiter system and onto Saturn, another 20 months away. But before they left Jupiter, both voyagers closely examined the largest of Jupiter's moons, the Galilean satellites, satellites which were first discovered almost 400 years ago. In 1610, Galileo Galilei discovered what he first thought to be 4 new planets, planets which no man had ever seen before. He noted that they seemed to be captured in orbit around Jupiter, forming in essence a miniature solar system. In order of the distance from Jupiter, he named the 4 Io, Europa, Ganymede, and Callisto, all mythological lovers of Jupiter. Today, we know that these Galilean satellites are, in fact, the largest and brightest of Jupiter's moons.
The smaller 2, Io and Europa, are the size of our moon. The larger 2, Ganymede and Callisto, are as large as the planet Mercury. They presumably were born together 4.5 billion years ago and have been orbiting Jupiter ever since, but they are different in their initial composition, and they're different in the way they have evolved, the kind of geological processes, for instance, that have taken place on their surfaces. Starting from the outside, Callisto is perhaps the most familiar to us from our study of previous worlds. It is a body of low density, which means that it contains a great deal of water or ice mixed with rock, and this is different from anything we have seen before. Nevertheless, its surface is covered with craters due to impacts of infalling debris, very much like the craters on the Moon or Mercury. The surface is old because it simply would have to have stayed there a long time, being impacted to accumulate the shoulder-to-shoulder craters that we see now. There are differences from our previous experience, however, presumably because of the ice mixed with the rock. There are no high mountains, there are no deep craters, everything has been flattened out, as though the surface material actually flows. As we move in from Callisto to Ganymede, we see some parts of Ganymede that are very like Callisto. And in bulk properties, Ganymede is also like Callisto. It's a low-density, large object, a mixture of ice and rock. But the surface of Ganymede has undergone a lot of evolutionary processes that seem absent on Callisto. The old terrain is broken up, and in between are lighter-colored terrain, primarily ridges and mountains, that give the impression that there has been internal activity on Ganymede, that there has been a breakup of the surface, perhaps analogous to plate tectonics that move around the surface blocks on our own planet. Ganymede is the only other place in the solar system that we have seen evidence of these kinds of processes. Europa, the next in, is smaller and denser. It is more of a rocky body like our moon, but it apparently also contains a fairly large amount of water, and we suspect that water has come to the surface and creates something like a deep ocean with an icy crust on top. We don't really have a very good understanding of what the bizarre surface features on Europa look like. The surface seems cracked, broken up. Perhaps these are really basically like cracks in pack ice. Perhaps they represent other processes that we haven't seen before. The surface of Europa, we know, is nearly entirely covered with water. And in some ways, again, it is Earth-like in that it does have apparently a deep ocean and ice on the surface. Finally, Io is one of the most remarkable worlds in the solar system. It's an object the size of the moon and the density of the moon, a rocky object, but it clearly has evolved just about as different from the moon as it's possible to imagine. We think the main cause of this difference is strong heating of Io by tidal forces of Jupiter. Alternate squeezing and unsqueezing of the satellite that pumps heat into it at about 100 times the rate one would expect from other processes such as radioactive decay. The result is the interior of Io is completely molten. Only a thin crust of rock exists, and the interior, being molten, is circulating and comes to the surface in the form of a great deal of violent volcanism. We think these volcanoes that were discovered by Voyager are operating at a rate that would recycle the entire interior of Io in the 4 billion year history of the object. So many volatile materials such as water and carbon dioxide are gone completely. Others, such as sulfur, have been brought to the surface, and we have a bizarre world bright colors of sulfur, violent volcanoes shooting up plumes much higher than any volcanoes on Earth, and a surface that's entirely recycled and reworked by the activity due to the heating of the interior.
In a blurred but historic photograph, Voyager 1 also discovered a thin ring system surrounding Jupiter, the extent of which is shown here in this artist's conception. Voyager 2 was then reprogrammed to view the rings from the night side of the planet. Scientists were surprised once again by the brightness of the rings when lit from behind by the sunlight.
I was there, and it was spectacular, that's all. People ask sometimes, well, what do the rings tell us about the origin and evolution of the solar system? And people get very heavy on the science and all the rest of it, but one thing they tell us is that in spite of everything we've learned about the planets and the solar system, there are still wonderful things out there to be discovered. We were all just delighted to see them.
Just as Voyager's inspection of the Galilean satellites contributed immensely to our understanding of planetary geology, the thousands of images and non-visual measurements of the Jovian atmosphere have contributed heavily to an improved understanding of planetary meteorology.
One of the challenges has always been to explain why the cloud patterns on Jupiter look so different from the cloud patterns on the Earth. Let me point out some differences. Jupiter's clouds are banded. They are arranged in stripes. Secondly, these patterns last for years. The red spot has been around for centuries, as long as we've been observing it. And weather systems on the Earth don't last this long. So that's an interesting challenge. And I think one of the things that Voyager has shown is that the sort of fundamental structure is due to currents underneath the clouds. We had thought that, or at least many of us had thought that the clouds themselves were generating their own order and structure. But now we are seeing that although the cloud patterns change from year to year, the currents, eastward and westward currents, remain at the same latitudes year after year, in fact over 50 and 100 years.
But amongst those cloud bands are very interesting terrestrial analogues. Around the equator, along the northern edge, about 9 degrees north of the equator, is a train of features we call plumes. Some have bright nuclei with long tails stretching out for tens of thousands of kilometers. Now, what's so exciting about those is that they are probably related to cumulus convection as we find in the Earth's tropics. They are deep-seated, they stretch down for 50 or 60 kilometers to levels where there's water vapor to power them. But they're just like huge tropical storms. And they demonstrate the importance of wave motions in the Jovian atmosphere because of their regular spacing. There's no doubt in my mind, and obviously everybody else's, that the feature that's captured everyone's imagination is the Great Red Spot. I think we've spent too much time thinking about it because we've now looked at the Great Red Spot, the white ovals, and smaller scale spots in the Jovian atmosphere. And what we find is that they're morphologically the same. Their interior structures are the same. They all rotate in an anticyclonic way in the southern hemisphere and the opposite direction in the northern hemisphere. They all, to their west of these features, have a very important disturbance. You have a jet coming from the east, you get a jet from the west that gives you a turbulent regime. So we find that the interactions of these bodies gets weaker as they get smaller, but very importantly that they all perturb the atmosphere. Because they rotate anticyclonically, they are upwelling, they're bringing material from below. But the big difference between the red spot and those ovals is its colour, and the fact that we find divergence of the cloud tops, which implies convergence down below, is clearly an indication it's bringing material up from beneath the clouds. And the obvious candidate there is phosphine, which we have discovered with the infrared instruments being also measured from the Earth. And when that, of course, reaches the cloud tops, the action of ultraviolet sunlight will simply photodissociate it and through a set of chemical cycles produce red phosphorus. So there is one way in which we can explain the particular colour of the red spot. and why its colour then is different from the ovals is that it may be deeper. So here then you have features which relate to Earth's storm system. So they're the areas of upwelling, and of course if there are areas of upwelling there must be areas of downwelling. And a good example of this are the set of things we call barges. You find these as long, drawn-out, dark features. And it's evident from the infrared measurements and also by some of the time-lapse sequences we looked at that they are vortices with downwelling. We're looking to brown clouds which are 30, 40 kilometers below the visible surface, which are marked by the white Amelia cirrus.
I think that the biggest impact that Voyager has had on the public has been their ability to share in the excitement of a remarkable mission, peering into the dark outer reaches of the solar system and seeing worlds that are so bizarre that they often exceed the imagination of science fiction writers, and the public shared in that at roughly the same time that we did.
In the late 1980s, the space shuttle is scheduled to launch its first interplanetary space probe, Galileo. Targeted for Jupiter, the Galileo spacecraft will drop, for the first time, an instrumented probe which will make a detailed analysis of the Jovian atmosphere. Galileo's radio signals will be relayed by the remaining portion of the spacecraft, which will also orbit Jupiter and spend 20 months conducting an extensive series of experiments and close flybys of the Galilean satellites. Galileo is designed to make the most detailed observations ever of Jupiter's major satellites, which were discovered by its namesake almost 400 years ago.
We just received a stat clear message. Roger. Arc Incremental, verify command stack loaded, block message number 9, first command, IP Whiskey 2, time 141032.8. Roger, copy. We're enabling message 10 at this time.
Jupiter is the doorway to the outer planets, a class of planets very different from our own. And the Jovian planets are, in turn, a doorway to the imposingly vast reaches of interstellar space. Like a child, we venture farther and farther from home as the years go by. With the early missions, Mariner and Apollo, we stayed close to home. Adolescence was in the form of the later missions to the outer planets, Pioneer, Voyager, and soon Galileo. But we're still years away from maturity, the ability and confidence to venture through the doorway of the outer planets and into the void of interstellar space.